Hi class, in this lab, we will practice how to separate a mixture of different components. So this will allow us to apply the difference of the some of the property, mostly is a physical property of different components. And after that, after we go through those the basic introduction about those separation scales or separation tools. Separation, say, separation tools or methods. And you will design a unique way or sequence to separate the mixture of different components. Let's say that what kind of method we can apply to separate the molecules. So what kind of property we can apply to separate them. So here are the list of different separation techniques. Well, we can also call separation methods. Or we can also call them as the separation tools. So the first one is the dissolution and the filtration. Then we will look at the evaporation, crystallization, sublimation, extraction, distillation, fractional distillation, chromatography. Now, among all those methods, some are very useful and are commonly used in the lab. And some methods are commonly used in industrial. All the methods we choose that will be depends on the, say, which one is easier to do. So easy to do. And also we will consider them as a cost of methods. And also we will call the adaptability for the actual use. For example, scale. So some methods probably is very easy and very efficient to separate the components, but it cannot be upscales. Example like the chromatography. Chromatography, normally we use that in the laboratory or the normally is a nasty method. We will separate something which we cannot separate with other methods, but this one is limited to very small scales, somewhere less than or somewhere about 1 gram or gram scales. You can only for gram scales. However, compared to that, if you do the distillation, this can go to large scale, particularly like the fractional distillation, even we can simply apply to the industrial, like if you travel around the city of Houston or neighbor cities, you can see a lot of those high towers. That's basically do the distillation and a fractional distillation. So those can work for the tons or tons, several barrels per hour. So those are large scales. Anyway, let's go through all those separation techniques one by one. Let's look at it here. So suppose you have a mixture of sulfur. So sulfur will be these yellow powders and iron. For example, iron is a powder as well. So if you mix them together, so which method you can use to separate them? Okay, here we will think about the way. So remember, I tell you we have to consider the cost of the method. Some methods are probably very easy to do, but very costly. You have to use the expensive reagent or expensive equipment. Some will be very easy. But for this example, if you mix them together, so let's see, like this case, we can simply apply the physical property of irons, which can be easily drawn to the magnet. And we can use the magnet to pull out of those iron from the sulfur, right? So in this case, we can separate, although this one cannot 100% separate them because some of the sulfur powders probably will be absorbed to the surface of the ions, but you can separate them in the large extent, right? Then later on we can separate them again. So this is the one way for the physical methods. Now let's look at the dissolution and the filtration. Dissolution, you can look at that here. We see the word of solution. That's solution means you will form a homogeneous mixture, right? So dissolution means that is a process. You can use a suitable solvent, this one, to dissolve substances from the mixture. That means if you have a mixture, some of the components are very soluble in one type of solvent, but the others are not. In this case, you can use the dissolution to simply separate them. For example, if you have a mixture of salt, in this case, the salt, we will typically mention that sodium chloride. And we know sodium chloride are very soluble in water at the level. So for example, sodium chloride can go to 32 grams per 100 gram or 100 milliliter of water. So that means if you have 100 milliliter of water, you can dissolve up to 32 grams of salt. And then you have some other things like the chalk or something else mixed with the sodium chloride. In this case, you simply can use water to dissolve sodium chloride and leave those things which insoluble. And then after that, you can do the filtration. Then after the filtration, we can get the sodium chloride back by removing the water by the evaporation or distillation, right? This is the process we call dissolution. Combined with the dissolution, we will see that the filtration. Filtration is in the filter, basically, right? So that means it's used to separate a large insoluble solid particle, must be not, right? Not insoluble particles from a liquid or can from a solution or from a gas mixtures. In this case, we asked that for the notch. The question is if you have a very superfine particles, even they are not soluble, but they will form a pad. So, and what difficult allow the liquid to pass through. In this case, that's the filtration is impossible to do. So then we will do look at the filtration. Here is a diagram to show the major component used in the filtration. So you can see this filtration apparatus. This one we will simply, this setting we will call gravitational self-filtration. Because this liquid will be drawn through the filter paper. Here you see this filter paper. You have one layer of filter paper, right? So liquid will be drawn through those filter paper by the gravity of the liquid, right? So, and here the bottom is clear, and you see those particles will stay here because for the filter paper, it generally is a piece of paper, and this paper there are many holes on the papers. And typically we want the paper, the holes are uniformly in size. So the holes size are similar, or actually even not exactly the same size, but very close to each other. In this case, then you can see, so if you have a particle, so this size, the size of the hole, we call porosity. We talk about the diameter of the holes. And this one, we will talk about that, how much you can stay on the paper. If the particle are smaller than the diameter of the holes, certainly those particles can pass through along with those liquid, right? Along with the liquid. Now, if the particle has the diameters is bigger than the hole, no matter what, they will not pass through. So anyway, we see these holes, actually you cannot use your eye, naked eye to see these holes because those holes are very small. Anyway, now, so here you can see this is a funnel. This is a funnel, right? So that's a filter funnel. And then we have a filter paper put here. And then we can have a conical flask or beaker that's basically put here to collect them. And then after that, you have used this the distilled water to wash them for that. So this one, you see that filter paper has a tiny pores, as I mentioned here, allows a small solvent liquid solute particles to flow through, right? And the solid particle will be trapped with the filter paper. We call residues, right? Now, this is the one way. This one normally works for those large particles. So if you have a particle, think about it. You have a particle very, very small, and it will be packed, form a layer of pack. So very difficult to cross through. So think about it. If you have some like a flour, you mix them as a gel or something, then you try to fill through, you see that it's almost impossible to fill through. Then we will have another type of setting for those filtration. Well, here we generally call it the vacuum filtration. The setup are very similar to that, but because we have to keep them under vacuum. So in this case, we will have those funnels. And so this we normally call Bush funnel. And here you can put a layer of filter paper. Then at the bottom here, you have a flask. And this flask normally is a thick wall. So they can tolerate the vacuum. And here we will connect to vacuum. Okay. And so this case, you can see funnel, make sure the opening are facing this hole, the opening, not the turnaround. Then you have the liquid. So the reason we use this one, because we can pour the vacuum, pour the gas here, reduce the pressure. So on top, we have an atmosphere pressure. So push the liquid goes through. So this way it will be much, much faster, right? Evaporation. So you can see evaporation. That's basically removal of solvent molecules in solution by heating a solution until only the solute particle remains. So this one generally applies to those low volume liquid. Here I simply use a liquid. So you can use that as a solvent. This typically used to apply, say you have some particles, you have a materials dissolved in solvent. Then after the filtration, your ideal compounds will stay in the liquid. Then you need to remove the liquid, so you can do evaporation. And this one, you can simply use a heat to remove that. And you can also use rotovac. Means rotatory evaporation. So this way will be much, much efficient. Okay, so, and another one is crystallization. This one we often use, and this one also you often used in industrial, because this you can use in large scale. So this involves, so think about this way. How the crystallization works. If you have a solvent, right? And we have some solute, for example, you have a solute, will be able to dissolve in solvent. However, the solubility, we will see. Solubility, that's talking about at certain temperatures, the maximum amount of solute you can put into the solvents. For example, we will say sodium chloride, like this one. We mentioned that you can put it roughly 32.6 grams in 100 ml of water when at the boiling water. So this is the amount you can put that. Then once you cool down, the solubility will decrease somehow. Then that cannot hold that much in the solution anymore. That's how they can gradually crystallize and separate from the solution. So this normally applies to the situation when you have the solubility has a sharp relationship. For example, here, if we have this relationship here, this one's the solubility, and this one's temperature. we know the higher the temperature normally is the higher solubility. So you want something have very sharp, like this relationship. Then that's when you can easily apply that for the crystallization, because at a higher temperature, you can hold this much. Here, this amount. But then once you cool down temperature, the difference in terms of the solubility, this will be forced out from the solution. Then you can recover. And the difference from the total amount of this one, that's talking about the recovery yield of the crystallization. So, but this method doesn't apply for the situation, something like this. Here, solubility, temperature. If something has a very slow, either case, so very slow change or even very slow change. Like this case is talking about no matter how high, you increase the temperature, solubility only increases slowly. So that means when you cool down, you only recover a small amount. So that means the recovery yield is you only form a few amount of crystals. It's not good for get the large amount of the crystals impure. Like this one means even they are very soluble in solutions, but even you cool down, the difference about the solubility is not big. So you still have a whole amount to stay in the solution. That means you still can only get this much out. So those in either cases is not good for the crystallization. So in order to solve the problem for those compounds, you have to choose different solvents, allows them to have a sharp like this relationship. So this is the way some compounds will show like you increase the temperature, their solubility actually decrease. There will be something like this. Something like this. So in this case, you also cannot apply for the crystallization to purify this type of compounds. Anyway, so crystals, after they form the crystals, then that's typically for those, as like this case here, we talk about. Like this case, very sharp, right? As you go down, gradually cool down, the particle will be getting bigger, bigger, bigger. So the larger the particle is easier to filtrate. So that will be easier for the later process. So the crystallization, that's when we mentioned that you remove a solvent molecule in a solution by heating solution until that is saturated. So that's how I show you, we'll have to go to, allow them to go to like a very high temperature. You have fully saturated, means they cannot dissolve much more than this solubility. As you cool down, they will gradually crystallize, right? So for the crystallization, you can see the process here. It's here, you actually impure solid. You have all those, then you add the solvent here, then you heat up, right? Heat up. So in this case, you will try to add some boiling solvents. And here, you don't use a boiling solvent, and here is a hot plate you can heat up and allow them to dissolve. In this case, there will be still something which is not dissolved in the solvent. Then you can do the filtration and to filter those insoluble materials. After that, then in this case, you continue to heating that, evaporate all those solvents and allow them to reach the saturated solutions. Then you let them slowly cool down, must be slowly cool down. The reason for slowly cool down is that way is to groove. So we will say groove crystals. So as the process slowly go down, and once there's some seed, we will call seeds. Then say you have a few particles, and those molecule of similar shape or similar molecular formula or molecular force. Similar, you can say similar formula anyway, similar molecular force will be drawn to the surface of this particle, they stay together, they aggregate, and gradually draw more molecule from the solution to here. So the crystals grew. Once you gradually lower the temperatures. But the question is, if you cool down quickly, then in this case, all those particles dissolve like a compound dissolve in the solutions, their solubility decrease, they can squeeze out from the solutions. So this case, they will form somehow will not form the regular shape to form the crystals. They will form amorphous solid. In this case, they will form so many superfine powders. In this case, they will not, even for this case, since the process of the precipitation is very fast, then those some of the impurity stay in the solvent will be wrapped inside of those particles. So you will not get a pure crystals or pure solid. But for this case, since this process of solution and dissolution is reversible, so some other impurities, once they draw to here, because their shape are not compatible with these crystals, so there will be dissolution, go back to solution. Only those molecules of similar shape or similar molecular force will be drawn together. So that's how you can get all of the same kind of molecules stay together. That's the way for the crystallization. Now let's look at extraction. Extraction is another process often used in the laboratory, particularly in the organic lab. Extraction is where we apply. So let's say that you say used to separate a mixture of two or more liquids that are immiscible. So for example, use the oil and the water. So for example, here we will have a separating funnel, something like this case. And here you have a switch, so you can allow, so this you can allow them to stick from the bottom. Then you have a two layer of the liquid, and those two layer of liquid is not miscible, so we will call them immiscible. So that means they cannot go to one layers. In addition, one will be heavier than another, so one has higher density than the other. In this case, you have two solvents. For example, once we have a methylene chloride versus the water. And this water, we know that the density is about 1 gram per milliliter. And the methylene chloride, this one is 1.4 gram per milliliter. So you will see when you have those two, this is the organic. So this will stay at the bottom and this will stay on top. Now, this is the one way. So, and then your compounds, according to their compatibility, so which one is more compatible with the water, with the methylene chloride? For example, water are more polar, so this case we apply like dissolves like. That means that if you have a polar solvent, what dissolve a polar component? Likewise, nonpolar solvent will dissolve nonpolar components, right? Now, if that's the case, then you can see, for example, here, this one is a layer of CH2, Cl2, and this one is water. Then if you have a sodium chloride, for example, sodium chloride will go to the aqueous phase, but not go to this layer. Then you can allow them to drip and separate them. So that's what we often use in the lab. Now the question is here. This one actually we can talk a lot about this one. And for those two liquid here, we mentioned that not only just that they are not miscible and they will have different density. If their density are similar, then you cannot separate them, right? And also that both liquid have different refracting index. In this case, you can clearly see the boundary. If both liquid have the same refracting index, then you cannot see the boundary. Okay, so this is the one way. Now let's see a last one. So if you still use water, often we use one water, and another case we can use like this one, diethyl ether. In this case, the density, this one still 1 gram per mil. But the ethyl ether, this one only around 0.75 gram per mil. So in this case, organic layer will stay on top and the aqueous layer go to the bottom. So you can choose that which solvent you will use that to combine with water for your separation, right? So those are the attractions. So you can choose. There are so many different solvents to choose with. So that's this one depends on the compounds. In addition, during the extraction, you actually can change the compound's solubility. For example, here. So for example, you have this one. Let's see. Phenol. Phenol is an organic compound which is not likely to dissolve in water, but more like an organic solvent. So in this case, if you have a mixture of this one with another mixture, for example, here, amine, right? So if you try to separate those two, for example, now what happened? This one, what you can see, so let's see a lot of compounds. You have a three of the mixture, and you try to separate them. This way, many other methods it doesn't apply because they cannot be used to separate this type of molecule. So in this case, extraction will be the best method because you can adjust their solubility in the solvent. So if suppose we use a combination of water versus ethyl ether, right? So this case all are soluble in the ethyl ether. In this case, they can dissolve that. However, if you apply some of the acid, for example, add the ethyl chloride to the solution water, then this will be protonate. So you have a protonate. Then you can see what happened. This will be protonate. Then this will become a soluble in water, but not soluble in ethyl ether now. So in this case, this one can go to the aqueous layer. You will be able to separate that. Now after that, you have only two left, this one and that one. But this one still not soluble in water. Then you can apply sodium hydroxide to change them to phenoxide, for example. Now this become a very soluble in water, not soluble in ethyl ether now. So you can separate this one again and only left this in the organic phase. So you can see that there is a lot of things you can do for the extraction. So here is the extraction. You see, as I show you, this is the separation funnel. Normally at top, we will capture that. So, but when you try to open this one, you have to leave this open. Otherwise, the pressure will hold them. You will not, they will not break through, right? So you see the two layers normally show different color or because of a different refraction index, you can see the boundary. So that's how you can separate them, right? Now, distillation. Distillation also often used in organic lab. Like like I said earlier, if you go to the Pasadena or Freeport, you see a lot of high towers. Those basically for the distillation, right? So these are used to separate a mixture of a miscible liquid as the boiling point are far apart. So here, let's see why we need that far apart, right? So say you have two solvents, two liquid. One say hexane. Hexane has a boiling point roughly about 90 degrees. And then you have another one, for example, creosote. This one has a boiling point of more than 200. So you can certainly to heat the temperature above the 120th, allow this to vaporize, and then you can remove that. After that, you can remove another one. We ask them the boiling point that you see far apart from each other. If they are very close, then they can vaporize at the same time or go to the vapor pressure, then vapor phase. So you cannot separate them anyway. So that's how we ask for that. Now this distillation apparatus, you can see that it's a distillation unit flask in the laboratory setting and a thermometer to measure the temperature. Basically, it's measure the melting boiling point, right? And then we have a condenser and the boiling stone, this one used to prevent the bumping. Okay, let's see that. So for example, here, You can see you put your mixture here in this flask. That we call a distillation flask. And this basically allows better separation for this. We have some like beads put inside it, either glass or wool or some kind of like cotton. You can put that, just allows them to exchange it for the heat, right? So you can see this case, the solvent molecule evaporate the heating and move into the condenser. So the notice here, this one's a condenser. We have a cold water in and out. You will not go other way around, not go this way, not go that way. So here you can see those low boiling point liquid will vaporize, go here because they once they vaporize, the pressures are higher, push them out. Once they go here, because you have a cold water goes through that, they will be condensed to liquid, so they can drop off here. So you can collect them and gradually, so you can separate them, right? And for the high boiling point component, once go here, because the boiling point is so high, the air probably can condense them down. So gradually you can separate them, right? So for this experiment, after we introduce different methods for separation, so this lab we provide you a mixture of iron and oleic acid. This one is organic molecules. Organic molecule. At this level, you just think about here. So this is the only organic molecule, and this one's sand, right? And the zinc oxide, this one, and sodium chloride. Now you have to analyze what's the difference between all the 5 components. And typically we will say organic molecules are soluble in organic solvent. This we can apply alcohol. For example, isopropanol. So this can separate the oleic acid out of others. Now, and this one is a solid. This solid, 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 right? And this solid. And this one is kind of close to solid and liquid. So once you have the mixture, you needed to develop. So let's see. Okay, you needed to develop a sequence of separation methods that allow you to separate them one component at a time. So each time you will separate one out from each other. So this case, so for example, here, since this one, I will suggest you here, my suggestion is this oleic acid, that's organic, and the others not dissolving organic. You can apply the organic to this one as a mixture. You can do the vacuum filtration. Organic will wash off this one, right? Wash off that. Then you can see now here we give you the mixtures. So after you wash off, so for example, we do the filtration like a vacuum filtration, right? You hear the funnels and all those. So the bottom we collect the isopropanol and this one. Then we need to evaporate the isopropanol, get the mass of the oleic acid, so you can tell how much of the oleic acid there, right? So after that, you will have the mixture of here. So this one's not there anymore. So you have the iron, sand, zinc oxide, sodium chloride. In this case, you have to design a lot of methods. So which way will be only separate one from the other. So you can think about which methods you will be able to separate that. So now so up to here, I will not tell you, I will ask you to think about that and develop the methods and come to the lab to verify with me before you start your experiment. This is what I can tell you right now, up to this level.